Okay, so for today, the stuff that we've been doing, the piecewise function stuff it's kind of just a separate thing. It's just one little unit, and then one little section in Unit 3, and then the rest of it is quite different. The rest of it is all pretty uniform. It all relates to itself better than that. One section is kind of just an oddball outlier. Okay, so I would say this stuff is more important than that. I mean, the piecewise functions are important, but I'm not sure I want to spend a ton more time on piecewise functions. I can go through another example tomorrow, and I'm happy to do that, give you one last look at it. But after that, we kind of got to move on to this stuff. So parent functions. Here's what we mean by a parent function. In math, when we talk about a family of graphs or a family of functions or a family of curves, anything like that, they're going to be functions whose graphs have similar characteristics. Okay, and the simplest member of that family is what we call the parent function. That's the most basic vanilla version of a given type of function. So let's get, phone should be away, please. Get away. So we're going to look at 8 today. And we're just going to describe what the graphs look like and what the characteristics are. And this is actually pretty easy stuff. This is just the math equivalent of memorizing some state capitals. It's really not anything high level here. Why are we doing this? Well, we're doing this because the next step we're going to take, once we know what these parent graphs look like, and we're really going to focus more on absolute value functions and then eventually quadratic functions. But later on in the year, we'll hit all of these at some point. At least between this year and next year, you'll hit all of these at some point. And we're going to be able to take any of these parent graphs, and we're going to be able to do some transformations of those parent graphs to tweak the graphs in ways that we want to. There's 4 different things we can do to create more complex graphs from the parent graph, from the parent function. We can translate the graph horizontally and vertically. Okay, so we can move it around on the XY plane. We can stretch or compress it vertically. Okay, and then we can reflect it vertically. And by doing those 4 things, we can take the most simple parent graphs and we can create more complicated versions of them. Okay? But the first step is we just want to understand how do these parent graphs, what do they look like and what are their characteristics. So first piece of good news here is we can just cross one of them off. Linear, we're not going to deal with. Linear, you guys are great with graphing lines. We don't really need to think about linear equations in terms of a parent graph. It's really not that helpful. But the other ones, it is helpful. So we'll start with an absolute value function. So here's our most basic form of an absolute value function. F of x equals the absolute value of x. Simple as it can get. So the shape of that graph, to get the shape of the graph, all we're going to do is we're just going to pick some points and plot some points and see if we can get a trend here. So what's f of 0? If I plug 0 in for x, what do I get back? 0. Square root of 0 is 0. So we know we're going to get a point with coordinates 0, 0. What about f of 1? 1. Absolute value of 1 is 1. So if we go over 1, we go up 1. What about f of negative 1? 1. Good. What about 2? F of 2? 2. And so you can already kind of see what's going on. We're going to get a straight line here, and we're going to get a straight line there, and it's a V-shape. That's it. So an absolute value graph is a V-shaped graph with the vertex at the origin, the point of the V at the origin. Okay, so based on that graph, what's the domain? What do you think? The x values. But I want the set of all the possible x values that would exist on that graph. All reals, isn't it? If I zoom out forever, the graph is going to go to the left forever and to the right forever. So the domain is all reals. Now the range is not all reals. The range definitely has some limits, right? What about the y values? Greater than or equal to 0. There you go, right? The y values start at 0 and go up forever. Good, you guys are getting this. That's good. So what's the x-intercept of this graph? Written as an ordered pair. 0, no. 0, 0. There you go. What about the y-intercept? 0, 0. Yeah. Okay. So the 1 point serves as both. The maximum number of roots or zeros. This is kind of a weird one. What this is saying is, if I took that parent graph and I made it more complex, what's the most x-intercepts it could ever have? When we talk about zeros, real zeros are just x-intercepts. Well, would you agree, kind of use your imagination here, if I took this v and I translated it down, the v could cross the x-axis in two places, right? So it could have as many as 2 zeros. In this case, it's only got one, and it could have none. If I push it upwards so that it never crosses the x-axis, it'd have 0 roots, or 0 zeros, okay? X-intercepts. Now, end behavior. Okay, this is another little different kind of a topic. You probably haven't talked about stuff like this before. End behavior wants to know what's going on with the extremes of the function. So as x approaches positive infinity, now what's that mean? X is the horizontal variable. So as I go to the right forever, infinitely far, we want to know, as that's happening, what's f of x doing? F of x is just y. So as I go to the right forever, what's happening with the y values of the function? They're going up forever, aren't they? So as x approaches infinity, f of x, or y, approaches infinity. Okay? What about as x approaches negative infinity? If I go to the left forever, what's y doing? Is it?
Positive.
Positive infinity. It's going up, isn't it? So it's positive infinity. Good. And then is this function continuous or discontinuous, do you think? It's continuous, and it's a simple test. If I can draw the graph without ever picking my pen off the board, it's continuous. Okay, so there's our absolute value graph. Okay, shifting gears. Quadratic function. The simplest quadratic function is the function f of x equals plain old x squared. From last year, what does that look like? Y equals x squared. Yeah, okay, good. It looks at parabola. It's kind of like a U, doesn't it? And we could plot some points. What's f of 0? 0. Good. So it goes through the point 0, 0. What's f of 1? 1. Yeah, 1 squared is 1, isn't it? So it goes through the point 1, 1. What's f of 2? 4. Good. 2 squared is 4. So it goes through the point 2, 4. And if I plug a negative number squared is always positive, isn't it? So wouldn't you agree if I plug in -1, I'm just going to get 1. If I plug in -2, I'm just going to get positive 4, right? And so we end up with, here's what this one looks like. And you already told me, right? It looks like it just looks like a U. So kind of like that, right? There's my parabola. Okay, what's the domain of this parabola? All reals, yeah. If I zoom out forever, it's going to go forever to the left and forever to the right. Okay, what's the range? Greater than or equal to 0. Good, y is greater than or equal to 0. What's our x-intercept? 0, 0. What's our y-intercept? 0, 0. The maximum number of roots or zeros, what do you think? Thank you. 2. Yep, it's 2. If I push this thing down, I could get up to 2. End behavior. As x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches positive infinity. Good. And it's continuous, isn't it? Okay. So what about cubic function? So cubic function is just f of x equals x cubed. Okay? So what's f of 0?
0.
0. What's f of 1?
3.
No. What's 1 cubed?
Oh, 1.
1.
Whoopsie daisies. I had 1
Okay, what's f of 2? 8. Yeah, 2 times 2 is 4 times 2 is 8. Good. So we'd have to go over 2, and we're going up off the chart here. So clear up there, we're at the point 2, 8. What's f of -1? -1 cubed. Well, -1 times -1 is 1, times -1 is -1. What's f of negative 2?
Yeah.
Negative 8. Okay, good, so we get the point. Negative 2, negative 8. And look what we get here. It looks kind of like that, right? So what's the domain of this one? If I zoom out forever, it's going to go to the left and the right forever, isn't it, right? And the range? Well, look at that one. What do you think? All reals. Yeah, it goes down forever and up forever, doesn't it? The x-intercept is getting boring. 0, 0. Y-intercept, 0, 0. Okay, the maximum number of roots. This is a bizarre one. The maximum number of roots on this one is one that's hard to see. The answer is 3, and here's why. I'll just give you a quick explanation. It's 3 because if I were to do a much more complicated version of a cubic function, it could look like this. And so it could have up to 3 x-intercepts. Okay. You can't really tell that from the parent graph. Okay. But that's the answer for that one. End behavior, you can tell this. As x approaches positive infinity, f of x approaches positive infinity. If it goes to the right forever, it goes up forever, doesn't it? As x approaches negative infinity, so as it goes to the left forever, it goes down, so f of x approaches negative infinity. And this one's also continuous. Okay? All right, so now we just did squared and cubed. Squared, y equals x squared and y equals x cubed. Now we're going to deal with the roots, similar roots. So square root graph. Square root graph is f of x equals square root of x. Okay, so what's f of 0? 0. What's f of 1? 1. Square root of 1 is 1. Okay, now what's the next convenient value for me to input?
5.
No, square root of 5 would be a decimal. What would the next one be to the right? Like square root of 2 is a big old ugly decimal. Square root of 3 is an ugly decimal. 4. Square root of 4 is 2, right? So we could input a 4. If we input an x value of 4, the output is 2. So what points do we get so far? Well, we get the point 0, 0. We get the point 1, 1, and we get the point 4, 2. Can I put negative values into a square root? I can try, and I can do it, but I'm not going to get a real result. And if we're only limiting ourselves to real numbers here, which we are, I can't do negative numbers. Remember, that's one of our 2 rules for real numbers. I can't divide by what? I can't divide by 0, and I can't take a square root of a negative number, right? Or any even root of a negative number. So the entire graph just looks like this. So now, what's my domain this time? X is what? Greater than or equal to 0. Exactly. Starts at 0 and goes to the right. What's my range? Y is greater than or equal to 0. Yeah, there you go. Okay, so what's my x-intercept? 0, 0. My y-intercept? 0, 0. Maximum number of roots is 1. Now my end behavior is really only one end on this function. As x approaches infinity, f of x approaches infinity. Okay, now the notes officially give us another end, but this is really not what we're looking for with end behavior. We'll add it anyway. As x approaches 0, what does y approach? What y value are we approaching there? 0. Right. Okay, but that's not that important. We already know that that's the x-intercept. Really, the one that's important is x, as x approaches infinity, y approaches infinity. Okay. So now cube root. So cube root graph, that's going to be f of x equals cube root of x. So let's make plot some points here. F of 0 is 0. F of 1 is What's the cube root of 1? 1. Yeah, and how come? Because 1 cubed is 1. So we get the point 1, 1. What's the next convenient one for us this time? Cube root of 3 is a decimal. Cube root of 5 is a decimal. Cube root of 9 is a decimal. The square root of 9 is 3, but not the cube root. What is it? 8. What's the cube root of 8? 2, because 2 cubed is 8. Okay, so we'd have to go over 8 and up 2. Okay, what's the cube root of negative 1? Is there a number? Now, it didn't work for square roots, right? Because what number squared is equal, what number squared equals negative 1? Nothing does, right? Anything squared is positive. But if I cube stuff, I can get negative results. What's the cube root of negative 1? What cube equals negative 1? Negative 1. That's it, yeah.
Big brain.
So we got the point negative 1, negative 1. What would be the next convenient point?
Negative 8.
Negative 8. Negative 8 is negative 2 cubed, isn't it? So we go, so there's our point, negative 8, negative 2. And this one looks like that. Okay, so what's the domain? All reals. What's the range? All reals. X-intercept, Y-intercept. Maximum number of roots or zeros is 1. End behavior, as x approaches infinity, f of x or y approaches infinity. As x approaches negative infinity, f of x or y approaches negative infinity. Continuous, good. Okay. Finally, this is a weird one now. We get down to reciprocal. Reciprocal is pretty strange. So the reciprocal graph looks, that's this function. F of x equals 1 over x. Okay, let's plot some points. What's f of 1? 1. Okay. What's f of 2? 1/2. Okay. I'm only gonna put the coordinates on this one. That's the really important one. What's f of 5? 1/5. What's f of 1,000? What's f of 1,000,000,000,000? 1 over 1,000,000,000,000. 1 trillion. Is that a big number?
No,
That's very, very small, right? So what's happening here, we can already answer one question. As x approaches infinity, as x approaches a very, very large number, what is the output of the function going to approach? No. What's it going to be? 0. Because look, I'm getting 1 on the top and enormous numbers on the bottom, and those are fractions that get tiny, 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 don't they? Right? So as x approaches infinity, f of x approaches 0. So we can already see that to the right, it's doing that. Okay, now what if I plug in a value 1/2? What's 1 divided by 1/2? If I divide by a fraction, I just flip and multiply, right? So f of 1/2 is 1 divided by 1/2. That's just 2, isn't it? What's f of 1/5? 5. What's f of 1/1000,000,000? Billion, right? F of 1/1,000,000,000 is 1 billion. So as values approach 0, as an ant's walking back towards 0 along this function from the right, he's just going up to spectacularly big numbers. And so it's going to do this, right? This function is just going to go like that. Okay? We could do the same thing for negative numbers. What's f of negative 1? 1 divided by negative 1 is negative 1, sure. So we get the point negative 1, negative 1. What's f of negative 1 billion? -1/1 billion, so I get a teeny tiny negative number, right? So it's gonna do this again, isn't it? It's just gonna do that, isn't it? Okay. And so this function looks really bizarre. What's the only x value that we never get to? 0, right? We never get to 0. And how do we describe that? Well, we say that there's what we call a vertical asymptote right there. And what in the world is that? A vertical asymptote, that's just that word right there. A vertical asymptote just means it's a line that the function approaches but never gets to. And this goes back to that discussion we had earlier in the year. If I cut my distance to the door in half every second for eternity, I still never get to the door, right? I'm always moving towards the door, but I never get to it, right? That's the limit of my motion. In the same way, this function, it's approaching the vertical line on the y-axis, x equals 0, but it never gets there, right? So the domain is x cannot equal 0. Any other x value is fine, but it can never be 0. What's the range? Is there a y value we can't get to? 0. Same deal, right? We get an asymptote, the vertical asymptote here is just the line x equals 0. But look, there's also a horizontal asymptote. Right here, there's another line. The x-axis is the line that the function approaches horizontally, right, as we move to the right and the left. And so we get another asymptote, y equals 0, that we never get to. We get infinitely close to, but never get to, okay? So what's my other end behavior? As x approaches negative infinity, what does y approach? 0, right? I mean, it's gonna be very small negative numbers, but it's always approaching 0, isn't it? Now, is this one continuous or discontinuous? Can I graph it without ever picking my pen off the board? No, I have to. I have to graph this part, pick my pen up, and graph that part, right? So this one is discontinuous. Okay? What do you think is the most important part, the most important point for making this graph, do you think? I mean, you might say it's 1, 1, or -1, -1. I would say the most important point for the whole thing is right there. It's a point that's not even on the graph. It's the point that's in between the two lobes of the graph where the asymptotes cross, right? Because once I know, if I know that there's a horizontal line through that point and a vertical line through that point, then it's pretty easy to graph this function, isn't it? Because of the asymptotes, right? Kind of weird. It's not even a point that's on the graph, but it's probably the most important point for graphing the function, okay? X-intercept and y-intercept. Is there an x-intercept? No, it never gets to the x-axis. Is there a y-intercept? No. Maximum number of roots or zeros is 1. Okay. All right, last two, exponential and logarithmic functions. So these are pretty bizarre ones too. An exponential function is anything of the form f of x equals some number to the x. So for example, we could do f of x equals 2 to the x, or f of x equals e to the x. What's e? When I write down a lowercase e, what do I mean? Do you know what that is? Have you ever seen that number before? It's like pi.
Energy.
It's like pi. It's called the natural numbers. 2.7128, blah, blah, blah. Goes forever. It's like pi. Okay. And we use it, we'll talk about this at the end of the year. This is really interesting, actually. This number shows up, this function and this function, exponentials and logarithmics, in some ways are the most important functions to deal with because they are the ones that model the way the world works probably the most. Like if you were to take, for example, a population of lemmings. Lemmings are just little rodents that live in Scandinavia. If you took a population of lemmings and you put them on an island, the lemmings would breed like crazy. Their population goes nuts. And the population would follow this exponential graph, exactly follow this exponential graph. until they ran out of food. Then they'd all die off. And that's what they do. They go in like 7-year cycles where these lemmings, their population explodes, and then they all die off, and there's very few of them. And then after a while, they kind of gradually build up again, and then population explodes, and they all die off again. It's crazy. That's what they do. We see it like jackrabbits in the United States do kind of the same thing. Now I want you to notice here, what's different about this? There's a really important difference between this exponential function and the other functions that we deal with that have exponents. Now look at our quadratic function and our cubic function. Notice we've got a variable to a power that's a constant. Quadratic is x squared, cubic is x cubed. Notice that the cubic function is a little more aggressive than the quadratic function. It starts to pick up steam, and it gets bigger faster than the quadratic function does, right? Okay, now compare that to the exponential function. What's different? Where does the exponent show up in the exponential function? It's not in the base, it's in the exponent, isn't it? Now think what that means. That means that as x increases, as the exponent gets bigger and bigger, what's that going to do to the growth rate of the function, do you think? It's going to go up faster and faster and faster all the time. And so what you'd expect is this thing's just going to start slow, but it's going to take off eventually. And when people talk about something, it's like, man, it's growing exponentially. What do they usually mean by that?
It's not going back.
Okay, and probably also they're meaning it's just exploding rapidly, right? It's growing really, really rapidly, out of control. Okay, so let's see if we can get some points on this one. It doesn't even matter what the base is. The basic shape of an exponential graph always looks the same. Now, from your properties of exponents, and we haven't really talked about that this year much, if at all, but you would have in Algebra 1. What if I plug 0 into this function? What's f of 0? Anything to the 0 power equals what? You remember? No? 1. Anything to the 0 power equals 1. So it's always going to go through the point 0, 1. Okay, what it's going to do to the left is it's going to be really small. So if we pick values, negative values, it's going to give us really small results. And if we pick positive values for x greater than 0, it's going to start to pick up steam very rapidly. So that's what an exponential graph looks like. Okay, it grows very slowly for a while, and then eventually it picks up steam and grows very, very rapidly. Okay? So what's the domain of this function? If I zoom out forever, won't it go forever to the left and forever to the right?
Yes.
So it's all reals. Now what about the range? Okay, I'll give you a little hint here too. The thing can never, it's got an asymptote here. So it never actually gets down to the x-axis. It never gets to 0. So what do you think it is?
Greater than.
Greater than, but not equal to. So just greater than 0. It couldn't actually be 0. Okay? The x-intercept, is there an x-intercept? No, none. It never gets down to the x-axis. Y-intercept? 0, 1. Yeah. Okay, maximum number of roots or zeros is 1. End behavior. As x approaches infinity, so we go to the right forever, f of x does what? Goes up forever. F of x approaches infinity. As x approaches negative infinity, what's y do? What's y approach? 0. Yeah, it gets really small. This one is continuous, and it has an asymptote at y equals 0. Now I'm going to go really fast on this last one, logarithmic. So logarithmic, we write like this. And here's how you can think about a logarithmic function. It's just the inverse, or kind of the opposite of an exponential function. So instead of going through the point 0, 1, it goes through the point 1, 0. Instead of starting off slow and picking up steam, it starts off incredibly fast growth and slows down. And so that's what it looks like. Okay, so its domain would be x is greater than 0. And how come? Because it's related, it's kind of the opposite of what the exponential was. The range of the exponential was y is greater than 0. So the domain of the logarithmic is x is greater than 0. The range is all reals, just like the range of exponential was all reals. The x-intercept, there is an x-intercept, it's at 1, 0, but this time there's no y-intercept, it's the opposite, right, of the exponential. Maximum number of roots or zeros is 1. As x approaches infinity, f of x approaches infinity, doesn't it? Go to the right forever, we go up forever. We can't go to the left forever, but as x approaches 0, you see that this thing shoots down forever,
Yeah.
right? And so f of x approaches negative infinity. Okay? It is continuous, and the only asymptote on this graph is the y-axis. So x equals 0. Okay? It's a lot of stuff. That's it. Okay? So on Friday, I'm going to give you an opportunity to have a really, really high test. Here's my Christmas present going into Christmas. We're going to take a quiz over nothing but this stuff. All you got to know is just remember those things. It's going to be a memorization quiz. No math to do. You just got to be able to fill in the blanks with all this stuff.
Will it be like just the piecewise?
No, not on Friday. It'll only be this stuff. There is an assignment on Moodle, which is just practicing memorizing this stuff, is all it is.